Welcome to Tech Girl Kannada YouTube channel. Module 4 Trees. Terminology, binary trees, properties of binary tree, array and linked representation of binary tree traversals, Inorder, Postorder, Preorder, additional binary tree operations, thread at binary trees, binary search trees, definition, insertion, deletion, traversal searching, applications of trees, evaluation of expression, programming examples, linear types of data structures, strings, array, lists, stacks, and queues. Non-linear data structure is a tree. This structure uses to represent data containing hierarchical relationship between elements. Data are organized in hierarchical manner. Records, family trees, table of contents. Tree. A tree is a finite set of one or more nodes such that there is a specially designed designated node called root. The remaining node are partitioned into n is greater than or equal to 0. Disjoint sets T1 to Tn, where each of the set is a tree. T1 to Tn are called subtree of the root. Every item in a tree is a root of some subtree of the whole. A node stands for the item of and from plus the branches to other nodes. The tree has 13 nodes. Root is A. Then B, C, D, E, F, G, H, I, J, K, L, H, I, J, K, L, M. Level 1, 2, 3, 4. What is the degree of the node? The number of subtrees of the node. There are, except root, there are 3 trees. Degree of the node is 3. Leaf or terminal nodes. Nodes that have degree 0. Children of D are H, I, J. Parent of D is A. The nodes which are all reachable from the node X using only one edge are called children of node X. And node X is the parent of for all those children. Siblings, children of the same parent. Degree of the tree, maximum of the degree of the nodes in the tree. Ancestors of a node are called the node along the path from the root of that node. The root node, a node with integer in degree 0. First node in the tree. A level of the node is defined by letting the root be at level 1. If the node is at level L, then its children are at level L plus 1. Height or depth of the tree is defined as the to be the maximum level of any node in the tree. Example, depth of the tree. Representation of the trees. There are 3 ways to represent. List representation, left child, right sibling representation as a degree 2 tree. List representation is written as A, B of E, K, L, F, C, G. C, G and D. Information in the root node comes first, followed by the list of subtree of the node. List representation is given as like this. List inside the list. Then the figure for the data and pointers to the tree nodes. Children, since the degree of each tree node may be different. Use memory nodes A, varying number of pointers fields. Using this node structure is very wasteful of space. Developed 2 specialized fixed node size representation for tree. Both of these require exactly 2 links fields per node. Left child, right sibling representation. Data node, data left child, right sibling. Every node has at most one leftmost child and at most one closest right sibling. So that will be order of the children in a tree is important. So A, B, C, D siblings for B, C, and D. And then B has a leftmost child as E, F. C, G, and down. And for H, there's a right sibling that is I, J. Representation as a degree 2 tree. Rotate the right sibling tree in left child right sibling tree clockwise by 45 degree. Right child of the root node of the tree is empty. Left child, right child tree representation of the tree. Left child, right child trees are also known as binary trees. Represent any tree as a binary tree. Tree, left child minus right child, right sibling tree, binary tree. Tree that should be converted into left child, right sibling tree, then into binary tree. Here there is an empty tree, then tree with one node, tree with two node, binary tree, tree with three node, not a binary tree. This is also not a binary tree. This is also not a binary tree. It has more than two subtrees. There should not be any cycles. If B is a subtree, A cannot be the subtree of B. Then for binary tree T is defined as a finite set of elements called nodes such that T is empty, called the null tree or empty tree, or T contains a distinguished node R called the root of T, and the remaining nodes of T form an ordered pair of disjoint binary trees T1 and T2. If T does contain a root R, then the two trees T1 and T2 are called the left and right subtrees of the R. If T1 is non-empty, then its root is called the left successor of R. If T2 is non-empty, then its root is called the right successor of R. B is the left successor and C is the right successor of the node A. Left subtree of the root A consists of nodes B, D, E, F. Right subtree of A consists of node C, G, H, J, K, L. Any node in a binary tree T has either 0, 1 or 2 successors. Binary trees T and T dash are said to be similar if they have the same structure. The trees are said to be copies if they are similar and if they have the same contents at corresponding nodes. Characteristics of BT: degree of any node must not exceed 2. Distinguish between the left subtree and the right subtree. While for trees, the order of the subtree is irrelevant. Binary tree may have 0 nodes. Algebraic expression E is equals to A minus B slash C star D plus E. Every algebraic expression will correspond to the unique tree. Here algebraic expression also can be written as a tree here. Types of binary trees are strictly binary tree, complete binary tree, extended binary tree or two trees, binary search tree, full binary tree. Strict binary tree if the edges of every node of the tree is either 0 or 2. Each node can have maximum of 2 children or no children. That is strictly binary tree. Full binary tree. A full binary tree of depth k is a binary tree of depth k having 2 power k minus 1, where k is greater than or equals to 0. Complete binary tree. The tree T is said to be complete if all its levels, except possibly the last, have the maximum number of possible nodes. If all the nodes at the last level appears as far left as possible. Full binary tree of depth k will have the 2 power k minus 1 nodes. But in this, it will be the left and right children of the node k are 2 into k and 2 into k plus 1. If 2k is less than or equal to n, k has the if k has no left child. If 2k plus n less than or equal to n, if 2k plus 1 greater than n, k has no right child. Then the parent of k is the node k by 2. K is not equal to 1. K is equal to 1. K is at the root and has no parent. When considering from 0, left and right children of the node k are 2k plus 1, 2k plus 2. The depth dn of the complete tree dn with n nodes is given by dn is equals to log n to the base 2 plus 1 and considering level as 0. Depth dn of the complete binary tree will be log base 2 n with n nodes are given by like this plus 1 log base 2 n log n to the base 2 plus 1. Extended binary tree, 2 trees. A binary tree T is said to be a 2 tree or an extended binary tree if each node has an either 0 or 2 children. Convert it into a 2 tree by replacing each empty subtree by a new node. The nodes in the original tree T are now the internal nodes in the extended tree, and the new nodes are the extended nodes in the extended tree. Tree binary tree. There is no tree having 0 nodes. There is an empty binary tree. Trees do not distinguish between the order of the children left or right. Viewed as trees, they are same. A, B and AB are different since the first binary tree has empty right subtree while the second has empty left subtree. Skewed tree. Skewed to the left. Node representation using structure. Struct node int info, struct node nlink, struct node rlink. Type def struct node. Pointer variable root can be used to point the root node always. If tree is empty, the pointer variable roots points to null, indicating tree is empty. Node root equals to null. Tree is empty. The pointer variable roots points to null, indicating tree is empty. Node root is equals to null. ADT binary tree, abbreviated bin tree, is abstract data type of binary tree objects. A finite set of nodes either empty or consisting of a root node, a left binary tree and right binary tree. Finite set of nodes either empty or consisting of a root tree, left binary tree, right binary tree. Functions for all BT, BT1, BT2 belongs to bin tree. Item belongs to element. Bin tree create an empty binary tree. Boolean is empty if BT equal to empty binary tree. Return true, else return false. Bin tree make BT of BT item BK2. Return a binary tree whose left subtree is BT1, whose right subtree is BT2, and whose root node contains the data item. Bin tree L child BT. If is empty of BT, return else return the left subtree of BT. Bin tree right child of BT, R child of BT. If is empty of BT, return error else return the right child of BT. Element data of BT. If is empty BT, return error else return the data in the root node of the BT. Properties of binary trees. Maximum number of nodes. The maximum number of nodes on level of a binary tree is 2 power I minus 1. I is greater than or equal to 1. The proof is by induction on I. Induction base. Maximum number of nodes in a binary tree is 2 power I minus 1. I is always greater than or equal to 1. Induction base. The root is only node on level I is equals to 1. Hence, the maximum number of nodes on level I equals to I1 is 2 power I minus 1. 2 power 0 equals to 1. Induction hypothesis that I be an arbitrary positive integer greater than 1. Assume that the maximum number of nodes on level I minus 1 is 2 power I minus 2. That is induction hypothesis, induction basis. This the root is the only node on level I1. Maximum number of nodes are I minus 1, 2 power 0, that is 1. Induction hypothesis is that I be an arbitrary positive integer greater than 1. Assume that the maximum number of nodes on the level is I minus 1 is 2 power I minus 2. Induction step will be each node in a binary tree has a maximum degree of 2. The maximum number of nodes on the level I is 2 times the maximum number of nodes on the level I minus 1. 2 power I minus 1. Maximum number of nodes in a binary tree of depth k is maximum number of nodes on level I equals to 1 k 2 power I minus 1 2 power k minus 1. Then relationship between the number of leaf nodes and the degree 2 nodes. For any non-empty binary tree T, if number is the number of the leaf nodes, n2 is the number of nodes of degree 2. So n0 is equals to n2 plus 1. Proof. Let n be the number of nodes of degree 1 and the total number of nodes n is equals to n0, n1, n2. If b is the number of branches, then n is equals to b plus 1. All branches from a node of degree 1 or 2. b is equals to n1 plus 2 n2. n is equals to b plus 1. n1 plus 2 n2 plus 1. n1 plus 2 n2 plus 1 minus n0 n1 n2. n0 n1 n2. What is it means? It is a n. So the next n plus 2 n2 plus 1 minus n0 minus n1 minus n2. n0 is equals to n2 plus 1, hence proved. Array and linked representation of binary tree. Insertion and deletion of nodes from the middle of a tree require the movement of potentially many nodes to reflect the change in level number of these nodes overcome easily through the way of linked representation. Linked representation is a 3 parallel arrays, information left, right, and a pointer variable root. Information of k contains the data of node n. Left k contains the location of the left child of the node. Right k contains the location of the right child of the node n. Each node n of a tree will correspond to a location K root contain the location of root R of tree. If subtree is empty, then the pointer contain null value. If tree T itself is empty, root will contain null value. Like this. Then the linked represent appears in the memory as root aval 8. Information left child, right child will be like this. Then we will be having a while list is maintained as a one-way list using the array left. Array representation is good for complete binary tree. It is wasteful for many other binary tree. Array representation of binary tree, sequential representation of binary tree. This representation uses only a single linear array tree. Tree of n equals to null indicates the tree is empty. Even though T has 9 nodes, it requires 14 locations. Sequential representation of a tree with depth of will be require an array with approximately 2 power d plus 1 elements. This representation is inefficient unless stated that binary tree T is complete or nearly complete. 11 nodes and depth is 5. 64 elements. 2 power 5 plus 1 is 64 elements. 2 power 3 plus 1 will be 16 elements. Then traversing of the binary tree. Traversing a tree or visiting each node of a tree exactly once. A full traversal produces a linear order of the nodes in the tree. There are 6 possible combinations of traversal: LNR, LRN, NLR, NRL, RNL, RLN. Traverse left before right. That will be like a left node, right node, node left right. And right before left will be like node right node left node. 3 ways of traversing a binary tree, that is Inorder, Postorder and Preorder. Inorder traversal: traverse the left subtree of the R Inorder, process the root R, traverse the right subtree of the R Inorder. Void Inorder, node PTR, if PTR, in order of PTR left child, printf PTR data in order of PTR right child. Preorder: process the root R, traverse the left subtree of the R in preorder, traverse the right subtree of R in preorder. Void preorder, node PTR if PTR, printf PTR data, preorder of PTR left child, PTR right child. Postorder will be traverse the left subtree of R in postorder, traverse the right subtree of R in postorder, process the root R. Void postorder, node PTR. If PTR, postorder of PTR left child, postorder of PTR right child, printf PTR data. Preorder will be A, B, D, E, C, E. Then Inorder will be, Inorder traversal will be like D, B, E, A, C, F. Postorder traversal will be D, E, B, F, C, A. And for this tree, if you observe carefully, you will get to see preorder traversal for this. Will be root node first, that is A, then it goes to left, B, D, G, H, then it comes to C, E, J, F. Then a post order will be like G, H, D, B. Then again in here it is I, E, F, C, A. Inorder will be like Inorder G, D, H, B, A, C, E, J, F, E, J, C, F. This will be the in order. Then in order for this will be A by B into C into D plus E. Preorder traversal for this will be plus multiplication, multiplication, multiplication divided by A, B, C, D, E. Preorder, postorder will be A, B slash C into D into E plus. Preorder for this will be preorder. First comes root A, B, D, E, F, C, G, H, J, L, K. Then in order will be, in order traversal for this will be D, B, E, F, A, C, G. In order traversal D, B, D, B, F, E, A. Then G, C, L, J, H, K. Post order traversal will be D, F, D, F, E, B. Then again G, L, J, K, H, C, A. Properties of a preorder traversal obtained by scanning the tree from the left to rightmost terminal node is the last node scanned. Terminal nodes D, F, G, L, and K are traversal in the same order from the left to right in all three traversal. Property of postorder traversal: every descendant of any node n is processed before the node n. Algebraic expression traversal will be like this. First we'll go with the in order traversal. A plus B minus C into D minus E divided by F plus G minus H. That will be in order traversal. Then for preorder we have root into A minus B C divided by minus D E minus H F G H minus plus F G H. That is preorder. Then post order will be like A B C minus into then D E minus then F G plus H minus then slash then multiplication. In order traversal, since there are A nodes in the tree, in order is invoked 19 times for the complete traversal, that is A slash B into C into D in plus E. A node that has no action indicates that the node is added to the stack. A node that has a P of action indicates that node is removed from the stack. Call of in order value in the root is this 19 times call will be happened. 1, 2, 3. Then a node has no action indicates that the node is added to the stack. First value is plus, action nothing. Second value is star, nothing. It is going pre-order way, then we will be going to A, then nothing happens in the next step, then again a null. Value in the node is a, value in the node is, then slash printf this, then a slash b will be happening, then printf null, then b will be printf, then null again. This will happen in order of star, in order of star, in order of slash, then in order of a null, null, b null. For a there is nothing. Oh, this is traversing. A's left child is nothing and A's right child is also null. Then it again comes back to A. Okay, that is A. Then goes to B. B also have nothing left. So again comes back to B. B's right also is null. Comes back to B. Then goes to the star. Then C. Then null. Then again C. It comes. Then again null. Like this it does traversals. Iterative Inorder traversal will be like void iter Inorder node ptr int top equals to -1 node stack of max size. Here there is an infinite for loop for nothing. Ptr should be there and ptr goes to ptr left child, push ptr, that goes to the stack, ptr equals to pop, then it gets deleted from the stack. If not ptr, break, then printf ptr data, ptr equals to ptr right child. Then the level order traversal. Traversal require a queue called level order traversal. Visit root first, then root's left child followed by the root's right child, visiting the nodes that each new level for the leftmost node to the rightmost node. Here it is like plus star E, then star D, then slash C, then A, B. This is the level order traversal. Void level order node ptr int front equals to rear equals to 0. We are using a queue, node queue of max size. If not ptr, return. Add a queue of ptr, then infinite for loop, ptr equals to delete queue. If ptr, then print the ptr data. If ptr left child, then print that left child as well. If ptr right child, then print ptr right child. Else break. They have given an order of the trees and we have to write the tree. That is post order, they have given it as HIDEBFGCA. We know that we have A. In order traversal, they have given this. Whatever there on the left side of A will be on the left tree. Whatever there on the right side of tree will be on the right tree. Then we will be finding that post order. What is there next is C. Then for C there is F and G. Then what is there after G and F? It is B. That will be on the left side first. Then if we check it on this side, HDI and E. HDI first come D in the post order. So D will be there. Then HI. Pre-order will be A, B, D, H, I, E, C, F, G. Then they have given another post order expression, that is I, E, J, F, C, K, L, H, D, B, A, and in order will be like this. First we will consider in post order the root node will be at the last, so that is A will be the root node, and in order as well, there everything is in the left side of A, so there is no right tree for A. Then we'll consider that. After A we'll be finding B from last, so B will be the next node, and then for B there are E, I, C, F, J and G, D, K, H, L on the right, so we are considering that. Then after B there is D, and where is D? It is at the right side of B, so we are considering D at that side. And there is only one node, that is G on the left side of D. And next will be H, that will be on the right side of D, so we will be putting right side H. Then there is L, that is right side of H, we are putting that, and K, that is left side of H, so we put that. Then we are taking it as K. After K there is G. Where is G? It is in between B and D, so we put there. Then there is C. Where is C? In inorder traversal it is left side of B, and so on will be done. And here they have given the pre-order traversal and the in order. We have to find the post-order traversal for that. Here for the above tree, the pre-order traversal will be A, B, C, E, I, F, G, A, B, C, E, I, F, J, D, G, H, L, L, H, K, L. Then for this, consider A as a root tree. On left side of the tree there is D, G and B. So the next thing will be B, so we'll be putting B as the next node. And then there is D, that is left side of B, so that we will be keeping that. And then there is G, that is also right side of the D. And then there is C, it is in the right side of the A, so we considered that, and so on. So for this, post-order traversal will be G, D, B, H, I, E, F, C, A. Then another question is given, that is homework for you. Pre-order info left, right, root. Initially push null onto the stack and initialize PTR. Set top equals to -1. Stack of 1 is null and pointer to the root. Repeat step 3 to step 5 while PTR not equal to null. Apply process to info of PTR. Right child is present. If right of PTR not equal to none, then push on stack. Set top equals to top plus 1. Stack of top equals to the right of PTR, end of if. Then again left child is present, then this is the pre-order traversal. It will be, if left of PTR not equal to null, then set PTR equal to left PTR, else top from stack. Set PTR equals to stack of top, and then top is equals to top minus 1. End of if structure, end of step 2 loop, then exit. In order traversal will be in order info left, right, root. push null onto the stack and initialize PTR. Set top equals to -1, then top equals to 1, stack of 1 equals to null and PTR equals to root. Repeat while PTR not equal to null. Push leftmost path onto the stack. Set top is equals to top plus 1 and stack of top equals to PTR, says the node. Set PTR equals to left of PTR, update PTR, end of loop. Set PTR equals to stack of top and top equals to top -1. Pops node from the stack. Repeat step 5 and 7, which PTR not equal to null, backtracking. Apply process to information of PTR. Then right child. If right of PTR not equal to null, then set PTR to right of PTR. Go to step 3. End of if structure. Set PTR equals to stack of top and top is equals to top -1. Pops node. End of step 4 loop. Exit. Post order will be info left right root. Push null onto the stack and initialize PTR. Then set top equals to 1. Stack of 1 equal to null. Then PTR equals to root. Push leftmost path onto the stack. Repeat step 3, step 5 until PTR not equal to null. Set top equals to top plus 1 and stack of top equals to PTR. Pushes PTR onto the stack. If right PTR not equal to null, then push onto the stack. Set top equals to top plus 1, stack of top is equals to right of PTR. End of his structure. Then set PTR to left of PTR. Update pointer. End of step 2 loop. Set PTR equals top of tab and top is equals to top -1. Pops node from the stack. Repeat while PTR is greater than 0. Apply process to info PTR. Set PTR and stack of top. Top equals to top -1. Pops node from the stack. End of the loop. If PTR is less than 0, then set PTR equals to minus PTR. Go to step 2. End of F structure, exit. In order will be like, first it goes from B to D. First data will be A, so it goes to leftmost node, that is the B, then goes to D, then goes to E as Inorder traversal, then goes to A, then goes to C, null data C null. Then preorder traversal will be plus, then next data leftmost node it is star, then again goes to star, then again goes to slash, then goes to A, null null, then goes to B, null null, then goes to C, then goes to D, then goes to E. Post order will be like this. This is for your understanding. Here it is illustrated. Then A plus B into C is written as a tree like this. And here the preorder traversal for this will be plus A star B C. Post order will be A B C star plus. Inorder traversal will be A plus B star C. A plus B star C. This will be like this. Using this, we can follow that. Binary search tree. A BST is a binary tree. It may be empty. If it is not empty, then it satisfies the following properties. Each node has exactly one key and the keys in the tree are distinct. The keys in the left subtree are smaller than the key in the root. The key in the right subtree are larger than the key in the root. The left and the right subtrees are The left and the right subtrees are also binary search trees. In case of duplicates, the value at n is greater than every value in the left subtree of n and less than or equal to every value in the right subtree of the n. Less than or equal to. It is not a BST because 22 has come on the right side of the 25. Other two trees are BSTs. With a BST, the first can be performed both by key value and by rank. Find the item with key K. Find the fifth smallest item. Delete the item with key K. Delete the fifth smallest item. Insert an item and determine its rank, etc. Traversal of BST is same as a traversal of BT. Searching a BST. Search for the node whose key is K. Begin at the root system. If the root is null, search tree contain no nodes and the search is unsuccessful. Otherwise, compare K with the key in the root. If key equal to root key, then search determined successfully. Terminate successfully. If K is less than the root key, then the elements in the right subtree can have a key value equal to K. Search the left subtree of the root. If K is larger than the root key value, search the right subtree of the root. Node search int item, node search int item, node root. If root equal to null, int item node root. If root equal to null, return root. If item equal to root info, then return root. If item less than root info, return search of item comma root link. So this is what you see in the recursive function. Return search of item comma root comma r link. That is else condition. If root is greater than, if item is greater than root info. Node search int item node root. Node start if root equal to null. Return null. Start equals to root. While start not equal to null. If item equal to start info. Return start. If item less than start info, start equals to start a link, else start equals to start r link. Return null. There are two functions where we are using while loop in this and recursive function in the first function. Inserting into a BST, duplicate elements will be there. Node insert int item, node root, node temp, start and previous. Temp is equals to get node where we are getting the node. Temp info equals to item, temp link null, temp r link null. Root equals to null, return temp. Previous equals to null, start equals to root. While start not equal to null, previous equals to start. If item less than start info, start a link, else start right link. If item less than previous, then if item less than the previous link, previous info. Yeah, if item is less than the previous info, then previous link is equals to temp. Else previous link is equals to temp. No duplicate items will be there. Then node to insert. Int item node root. Node temp start prior. Temp equals to get node. Temp info item. Temp link equals to null. Temp r link equals to null. If root equal to null, return temp. Prev equals to null. Start equals to root. While start not equal to null, prev is equals to start. If item equal to start info, printf duplicate items are not allowed. Free temp. Return root. If item is less than the start info, start equals to start L link, else start equals to start R link. If item equal to start info, duplicate items not allowed. Free time. Like that we have to do if it is the same item. Else this start equals to start L link, start R link. If item is less than the priv info, priv L link equals to temp, else priv R link equals to temp. Return root. Deletion from a BST. Deletion of a leaf is easy. Deletion of a non-leaf that has only one child is also easy. Deletion of a leaf is easy. Deletion of a non-leaf that has only one child is also easy. Okay. This is node delete item int item node root node start parent successor and the queue. If root equal to null, print tree is empty. Then parent equals to empty, start equals to root. Here parent is nothing but the previous only. Then start equals to root. While start not equal to null, item equal to start info break. Parent equals to start. If item less than this start info, start equals to start L link, else start equals to start R link. Then if start equal to null, item not found. Then case 1. If start L link equal to null, Q is equals to start R link. If start L link equal to null, Q is equals to start R link. Else if start R link equal to null, Q is equals to start L link. Then for successor equals to start R link, while successor L link is not null. Successor is equals to successor's L link. Successor's L link equals to start L link. Q equals to start R link. This goes to as find the inorder successor of the node to be deleted. Attach left subtree of the node to deleted to the left of the successor of the tree to be deleted. Obtain the right subtree of the node to be deleted. That is Q is equals to start R link. Successor is equals to start R link. Find the inorder successor. While successor L link not equal to null, it goes on till successor's L link. Then when the successor L link is equal to the start's L link, then the successor L link is equal to the start's L link, then Q equals to start R link. If parent equal to null, return Q. If start equal to parent L link equals to Q, else parent R link equals to Q. If start equal to parent L link, parent L link equals to Q, else parent R link equal to Q. Free start, return root. Attach the node of the parent, connecting parent of the node to be deleted to Q. Once the node is deleted, the ordering of the tree should be maintained. After deleting a node, elements in the left subtree should be lesser and elements in the right subtree should be greater or equal. Node 50 deleted here, where start. If we delete the node, then that successor and the queue will be here. So first we will be adding successor left it to parents. Start and link. 80 should come up. Then here if node 50 is deleted means then 90 will be coming here. Then 100 90 will be in the left side. Here also, if the node is deleted, then the 90 should come up to the left side of the 100. Then to that left, nothing can come. Where the left chain is empty, there this 20 will be going. For the successor, it is like this. Balanced search tree. The binary search tree is a binary tree in which for each node, say x in the tree elements, in the left subtree are less than info x, and elements in the right subtree are greater than or equal to elements in the x. Every node in the tree should satisfy this condition if the left subtree or right subtree exist. Algorithm to create binary subtree, search tree. Just now we learned this, all these things, hope you remember. Here in almost complete binary tree, the number of nodes that will be there is like n will be less than or equal to 2 power n, sigma 2 power n. Aerial trees. Two names, that is Adels and Belsky. These are people are Russian scientists. It's an ordered binary search tree in which the heights of two subtrees of every node differ maximum by 1. Height of the LST, height of the RST, 0 or 1 or minus 1. In aerial tree, each node is associated with a balanced factor. If this condition is satisfied by each node in the BT, then the tree is called aerial tree. Balance factor, height of the LST, height of the RST. Height of the LST minus height of the RST. In aerial tree, each node is associated with a balance factor. 0, both are same. Then 1 is height of LST is 1 more than height of RST. Minus 1 means height of LST is 1 less than height of RST. Here is an example of aerial tree. You can find the difference in their heights. Creating an aerial tree will be a repeated insertion of items into BST, but after adding each item in the tree, we have to check that must be made to ensure that the balance factor of each node is minus 1 or 0 or 1. Otherwise, rearrange the nodes in a tree. Algorithm, ABL insert of item root. Purpose to insert an item into an ABL tree. The item remains balanced after insertion. Input item to be inserted into the tree. Root of the ABL tree. Then output balanced tree with time efficiency of big O of log n base 2. Insert an item at the leaf level of an ABL tree as we insert an item into binary search tree. Trace backwards from the node inserted towards the root and compute the balance factors along the path. If the balance factor of each node in this path is 0 or 1 or minus 1, the tree is balanced and insertion is over. If we find a node whose balance factor is other than minus 1 or 0 or 1, consider this node and the two nodes below it in this path. If the three nodes considered in the step 3 are in straight line, apply single rotation. If the three nodes considered in the step 3 are in straight line, apply single rotation. If the three nodes selected are not in the straight line, apply double rotation. If there is a bend at the second node or like that, repeat 1 to 4 for all the items. Terminate. Once an item is inserted into the tree may be unbalanced. It is necessary to balance the tree using rotations. Types of rotation. single left rotation, single R rotation, double left right rotation, double right left rotation. So procedure to identify L and R rotation. Identify the first node where balance factor is not 0 or 1 or -1 in the path. While moving from node inserted towards root, identify two other nodes below the nodes where imbalance occurs in the path. If the node where balance's factor is other than -1, 0 or 1, then rotation is required. Left rotation, then identify which type of rotation is required. Then we will use left rotation. If the three nodes identified in step 1 and 2 are in a straight line, single rotation is required. If the factor of the node where imbalance occurs is in negative -2, then the tree is heavy towards right. So to balance it, we rotate it to left. X to Y, and then balanced will be like this. There is a left child for Y. So while we are rotating it, then we use the formula as Y will be at the top, X will be down, and then the item is inserted. After left rotation of X, purpose to rotate the tree left so that the tree remains in binary search tree input. The node X where left rotation takes place, output returns the root of left rotated subtree. The node X where left rotation takes place then returns the root of the left rotated subtree. Obtain the right child of the node to be rotated. Y is equal to right of X. Obtain the right child of Y. Z is equals to left of Y. Here this Y is equals to right of X and Z is equals to left of Y. Then rotate towards left. That becomes left of Y will become X, then right of X will become Z. Return the root of the left rotated subtree, that is return Y. Understood? That is left of Y equals to X, then the right of X equals to Z. Right rotation. When do we take the right rotation? If the three nodes identified in the step 3, 1 and 2 are in straight line, single rotation is required. If the balance factor of the node where imbalance occurs is 2, then the tree is heavy towards left side. We have to rotate it right. So we have rotated it as following. Imbalance item inserted. Then there is right child for Y. Then if there is a right child for Y, then while rotating towards right, the same thing we have to use. That will be replace left by right and right by left. That will be like right of Y equals to X and left of X equals to Z. That's it. Left right rotation. If the three nodes identified are not in a straight line, double rotation is required. Combination of two single rotation. Three nodes are not in the straight line. Assume X is a node where imbalance. Assume X is a node where imbalance occurs and Y is its child in the path. If the balance factor of Y is -1, this tree is right heavy. So rotate left at Y. Attach the parent of resulting subtree of X. Second rotation is required at X. Right rotation is required. Now here the balance factor is -1 for 40. Here first we should take left rotation. Before to insert an item 50, we have to insert it at right side of the 45. It is not in the straight line. So what we do is we will just do left rotation for 50 so that it becomes the inserting point should be left rotated. After left rotation, then 45 goes down, 50 comes up. Then we should do right rotation so that 50 comes up and 55 goes down. This is how we have to maintain the structure. Then RL rotation, replace -1 by 1, right by left and left by right. Tree is balanced. We have to insert 30. We will be inserting it on left side of the 35. It becomes unbalanced. Then we have inserted. Then the imbalance occurs. If you see the -2 and 2, then it is heavy in the left side. So we have to do a right rotation so that it becomes 30. Then it comes in the straight chain. Then we have to do left rotation. Construct an AVL tree by inserting the element 100, 200, 300, 250, 270, 70 and 40 successfully starting from an empty tree. In the similar way, the other two trees, AVL trees, are constructed. Efficiency of AVL tree depends on the height of the tree. Let us obtain a bound on the height of AVL tree having n nodes. The height of tree is balanced both above and below by logarithmic functions. Log n to the base 2 is less than or equal to height to the less than or equal to 1.44 into log n plus 2 to the base 2. In best case, tree may be complete binary tree, the height of which will be log n to the base 2. Worst case, tree may not be complete binary tree. The height of tree is 1.44 into the log of n plus 1 to the base 2. Worst case time complexity of searching and inserting an element into AVL tree is given by O of log n to the base 2. Search time required by AVL tree is almost same as search time required by the BST. Deleting an element from the AVL tree is more complex than to deleting an element of n log n to the base 2. Advanced search time, insertion time, deletion time efficiency will be always big O of log n to the base 2. Disadvantage, frequent relations, so more time, balance factor to be maintained, occupy extra space in the extra node of the trees. Deletion operation is complex. Even after deletion, the tree has to be balanced using rotations. 2 to 3 tree is a tree that has two kinds of nodes. 2 to 3 tree. 2 node contain a single key with two children, namely a left and right child. The left child serves as the root. Left subtree whose elements are less than key and VB. Right child, right subtree. 3 node contains two keys, K1 and K2, such that K1 is always less than K2 and has three children, namely left, middle, right. The left child serves as the root of the subtree whose elements is less than K1. Middle will be between K1 and K2. Right will be always greater than K2. Two to three tree is always height balanced. Height of 2 to 3 tree with respect to all these in a tree is same. or length of the path from the root to any leaf in the tree is same. Searching in a 2 to 3 tree always starts from root. Search in 2 to 3 tree with 2 node. If root is a 2 node, searching in similar as search in BST. Item equals to root node. Search successful. Item not present. Search either in a left tree or right tree. Encounter empty subtree and successful search. Search in a 2 to 3 tree with 3 node. In 3 node, each node has 2 items. Key, root search successful. Otherwise, search either left tree or middle tree or right subtree. Key less than the first item in the root, continue searching left subtree. Key between the 2 items in the root, search in between. Key if it is greater than the second item of the root, then search in right tree. Encounter an empty subtree, unsuccessful search. Creating a 2 to 3 tree, an item is always inserted at the leaf level. If the 2 to 3 tree is empty, insert only at the root level, except that first node, rest of the nodes are inserted only at the leaf level. By performing a search for the key to be inserted, appropriate leaf node is found. If the leaf node is a 2 node, compare the key item with the element ahead already in the node. If key to be inserted is less than the item already present, insert towards left of the old item, otherwise insert towards right of the old item. If the leaf node is a 3 node, split the leaf into 2 parts. Smallest item in 3 node is placed in first leaf, largest in second leaf, whereas the middle element is promoted to the place of the old 3 nodes present. If tree's root itself is a leaf node, in such situation, a new root is created to accept the middle. If the promotion of middle item to its parent leads to a 3 node, it may be required to split along the chain of leaves ancestors. By repeating this procedure, it is possible to create 2 to 3 tree. Here it is. For computing 2 to 3 nodes, we have like this. First C, we will be adding C, then COM, we have COMP. So we are having item as like this. It will be COMP UT, that is TU NOGI. Construct utility for the items like this. 9, then we will be adding 5, then we have to add 8, and so on. Thank you for watching. Do like, share and subscribe to my channel.